Okay, so welcome everyone to the second lecture by Marianna Russkikh, always from MIT, and I'll give it to her. Please, Marianna.
Thank you very much. So let me just remind you what is our goal from last time. So we're looking for embedding of the bipartite planar graphs such that the fluctuations of the diameter height function on such graphs, we want them to converge to the Gaussian free field. So given a big weighted graph, we are looking for the embedding of the dual graph in such a way that this embedding geometrically encodes weights that correspond to the same probability measure as a given graph, as a given weight, sorry, and this embedding defines the correct conformal structure in which the fluctuations of the height function converges to the GFF. And so we believe that the good candidate is t-embedding, or what we call circle pattern embedding. Okay, so and let me remind you two main results which we're going to discuss today. So first of all, we can prove the existence of t-embedding at least in the two following cases. If we deal with finite bipartite graphs with outer face of degree 4, or for any biperiodic bipartite graphs with biperiodic weights. And the second result is okay, indeed. If we already know that t-embeddings exist and we have a sequence of perfectly t-embedded graph, then under some technical assumptions and another assumption that some map which I'm going to define today related to the t-embedding is one issues in the limit, then the fluctuations convergence to the Gaussian free field. Okay. And let me also remind you what are our t-embeddings. So we're looking for the embeddings of graphs with the bipartite dual, and the important property, important condition is the following: that around each vertex of our embeddings, since the dual is bipartite, we can color faces in black and white in the just coloring weight. And then around each vertex, the sum of white angles is the same as the sum of black angles, and both those sums of cos pi. So this is the main condition of our t-embeddings, and this is what the t-embedding. So we're thinking about pictures like this with the angle condition around each vertex. Okay. So I said that we're looking for the embeddings which geometrically encodes weights that correspond to the same probability measure as a given weights. So how to define weights on t-embeddings? Let me also remind you. For each two adjacent faces W and B, we define the corresponding weight on WB as the complex number, which correspond to the vector between faces W and B. Or in other words, this is just a difference of the positions on the complex plane of the dual vertices of the edge WB. And first of all, note that those weights are Kasteleyn weights. So they satisfy Kasteleyn condition, which is that the alternating product around each vertex is either positive or negative, depending on the degree of the face. And so why this is so, recall that the ratio of such two vectors, the argument of the ratio of such two vectors is just the argument of this angle. And then if we're looking for the argument of the alternating product, then this is the same as the sum of arguments of white angles. And since it is pi, we obtain that Kasteleyn weights satisfy such weights defined on t-embedding satisfy Kasteleyn conditions. Okay, so now recall that the definition of t-embedding is equivalent to the centers of a circle pattern, right? Instead of definition of t-embeddings, we can just think that we're thinking about circle pattern realizations and the embedding of the dual graph, just the centers of corresponding circles. And using both definitions, we can check that t-embeddings satisfies t-embeddings are preserved under elementary transformations of the bipartite graphs. So it is known that there are three types of elementary transformations of bipartite graphs that doesn't change the probability measure on dimers. And here are they, those three local transformations. With respect to the change of weights on edges. And note that the first one for t-embeddings just correspond to adding one dual. In both cases, we just need to add a dual vertex. And for the t-embedding, this is just adding on a corresponding dual edge a vertex such that the ratio of length of these two edges is the same as the ratio of the corresponding weights. This one just corresponds to adding the diagonal for the t-embedding. Note that it doesn't change the angle condition, right? Because we just separate one white angle to two, and their sum is still the same. And for the black angles around this vertex, we just add one black face, which has angle 0, right? This is just a segment. And now to check that t-embeddings are preserved under this move, which calls the spider move or open renewal. We use another interpretation of the t-embeddings. Here we use the definition of t-embeddings as the centers of the circle pattern. And let me explain you why this is so for t-embeddings for the last elementary transformation. So there is a planar geometry fact, Mikhail theorem, and the statement is the following. Suppose that we have 4 circles, C1, C2, C3, and C4, as shown on the picture, with centers at U1, U2, U3, and U4. And consider the corresponding intersecting points, and assume that 4 of them are cyclic, so they lie on the same circle. Then, given such 5 circles, there exists a 6th one, or in other words, the other intersecting points in this case are also on the same circle, also lies on the circle. Okay, so this is Mikhail's theorem, and moreover, the centers of circles satisfy the following relation, where U tilde is the center of the 6th circle. And we call it a center move for the center. So if we replace this circle with this one, then this is how to compute the position of a new center. And indeed, this is this Michael theorem exactly correspond to the spider move. And the central move tell us that together with respect to the weight. So this weight change correspond to the central move for the centers of those circles. So okay, therefore Michael move for circle centers also correspond to the weight change for the under the urban renewal for the dimer model. Okay. So we just obtained that our t-embeddings are even nicer than we thought. We can define the weights in geometric way, and moreover, those embeddings satisfy, they are preserved under elementary transformations. Okay, now let us show the existence of t-embeddings. Note that the goal was to start with a given bipartite graph together with real valued weights, and to construct a t-embedding of the dual graph such that the weights defined geometrically, they are gauge equivalent to the given dimer weights. So let me remind you what is the definition of gauge equivalent weight. So the two weight function on edges are gauge equivalent if there exist two functions g and f, such that one weight can be written as a product of g, k, and the given graph, and those the given weight, sorry, and these two functions defined on white and black vertices. Okay, and the statement of the theorem is the following. For any finite graph with the outer face of degree 4, there exists a t-embedding of such a graph with the weights given by the embedding gauge equivalent to the initial Kasteleyn weights. And also for any biperiodic bipartite graphs with biperiodic weights, there exists a t-embedding of such a graph. Okay, let us discuss the first one in a bit more details to give you an intuition how to construct them, and also why it is important here that the outer face of degree 4, why we cannot do so far the general case. Okay, so note that here to find the embedding of the dual graph, it is the same as to find these two functions f and g, right? Because each, oops, because the embedding is just encoded by those weights, right? Each edge correspond to the corresponding Kasteleyn weights, and also recall that for t-embedding, the sum of Kasteleyn weights around each face is clearly 0, because this is just a sum of vectors around a polygon. So we're looking for gauge functions f and g, complex valued functions f and g, such that, first of all, they satisfy these conditions. This is exactly what I said just now, that the sum around each face is 0 of weights on a t-embedding. And also they satisfy some boundary conditions. So what are those boundary conditions? First of all, in the finite case, we're looking for the embedding of the augmented dual instead of the dual graph itself, which means that instead of one outer face, we associate to each boundary edge a boundary face. Okay? Or in other words, you can think that one just add to the bipartite graph an infinity vertex, and then you say that all boundary vertices are adjacent to the infinity vertex, and this is the dual graph of the bipartite graph together with this infinity vertex. Okay, so then the boundary conditions for the t-embedding are the following. We want to map those outer faces to some given polygon and to embed everything else inside this polygon. Then suppose that we start with the quadrilateral with outer with boundary edges given by vectors b1, b2, w1, w2. Then what we want on the boundary for our functions g and f, this is just the following condition. So instead of 0, we want the sum to be b1 or 2 or w1 or 2 correspondingly. Okay. Okay. So suppose that we find such a f and g, then we can define one form on edges. Note that this is a closed form since we have these two conditions. And since this is a closed form, we can define a function on vertices of the dual graph using this one form. And I claim that this map from the dual graph define the t-embedding. So we need to check that it is indeed an embedding. We need to check that these complex numbers, which we found as a solution of some nonlinear system of equations, then they indeed give an embedding, so there is no some overlappings. Okay, to prove this, we use the fact that t-embeddings are preserved under elementary transformations. And by the theorem of Postnikov, we know that for any bipartite graph with outer face of degree 4, we can simplify using elementary transformation the graph to just a single loop, to a single cycle of 4 vertices. So any graph with outer face of degree 4 can be simplified by elementary transformations to this simple graph with just 4 edges and 4 vertices. Then all we need to construct the t-embedding is construct the t-embedding of this one. And then using elementary transformations, we can reconstruct the embedding of the given graph. And okay, for such a graph and any face weight or any edge weights, there exists for any given quadrilateral, there exist exactly 2 embeddings, t-embeddings for this simple case. And then, okay, starting from one of them, we can use elementary transformations to reconstruct everything else. Okay, so what about boundary degree of, what about boundary outer faces of degree 2k, not 4? What we can do in this case, we can show that for each generic polygon, there exists a t-embedding realization, meaning that we can show that there exists a solution of that nonlinear system of equations. And as I said, in the case of outer boundary of degree 4, there are always exactly 2 solutions. And so in this case, we also have many solutions. So, but finitely many, but they're different. But we cannot show that the solution gives a proper embedding. So, and the problem here is that if you try to simplify a graph with outer face of degree more than 4, then this is not true that what you get will be just a simple cycle. You will get something more complicated. So minimal graphs for outer faces of bigger degrees, they're not always cycles, which means that still after simplification, you will have some big graph as bigger the outer, if you have a large outer face of a large degree, then you will get a big graph. And this is still a problem to show that the solution for that one gives an embedding. So anyway, here is an open question, whether the solution of the nonlinear system of equations gives a proper embedding, so that there is no overlappings. Okay. Now let me define the origami map. This is exactly the one which was in the theorem. We wanted it to vanish at the limit. So what is the origami map? And this is a very important object for t-embeddings. Okay, consider the, let us fix some, for example, white face. And to construct the image of the any other face under the origami map, we will do the following. Consider the face path from a fixed one to arbitrary one. And then the origami map is constructed in the following way. We just reflect the corresponding face with respect to the dual edges intersecting this face path. So we start with this triangle and we just consider the reflection of this triangle with respect to this dual edge. Then we continue, we take the image and consider the reflection of this one with respect to the next edge of the t-embedding. So we continue, and we stop. And for any other face, we just consider again the face path from the other face to the fixed W0 to get the map of that face. Now note that this definition doesn't depend on the choice of the path. So one can choose another path. And we will get the same map under this map, under reflections along this one. And why this is so? So, okay, reflecting again. Note that the t-embedding satisfies the angle condition. So, and since the sum of all black one is the same as all white one, and both of them are pi, then when we reflect the image of this green, red one, we will get exactly this blue one. So this reflecting procedure is consistent around the vertex, thanks to the angle condition of the t-embedding. And so under, clearly, if we just reflect everything with respect to this one, we get still the same. Okay, so in other words, we can just fix one white face, and then we fold the t-embedding along each edge. This is how to get the origami map from the t-embedding, and this is why we call it the origami map. Another definition of the origami map, which is also an important one, is given using the origami square root function. So what is the origami square root function? Let me define direction. Let me associate to each face some direction. So I will just, at each face, we can draw some vector of length 1. And those vectors satisfy the following condition. So their product, or better to say the product of their conjugate, is parallel to the direction of the corresponding edge of the t-embedding. So if this is our
Sorry, I'm a bit confused. Could you say again what is the origami map a map from, and what is it a map to?
So there are two ways to think about it. Either this is a map from the t-embedding to a complex plane, or you can also think about it as a map from the dual graph to the complex plane.
And so when you say a map from the t-embedding to the complex plane, you mean for each of these colored triangles, then you like take the center of the triangle and then, you know, do the origami map to it, and that gives you a point on the complex plane. Is that what you're saying?
Yep. So yet again, we fix one face. So the image of the under the origami of this face is just this face. So the points here just coincide with the image under the origami map.
Mm-hmm.
And then for any other point on t-embedding, for this one, let's say, to construct the image, like where is the image of this one? Okay, consider some path, phase path from fixed one to our one, and then do the sequence of reflections with respect to the corresponding edges of the t-embedding.
And so when you said that you could also view this as a map from the complex plane, are you saying, you know, instead of taking the center of this black triangle, you could take any points in this black triangle and then see where it goes?
I mean, like, I don't think about, I'm thinking about the whole triangle itself. So I take the whole triangle, don't think about center of this
Okay.
triangle. So this is just to indicate along which edge path, phase path, we are doing the sequence of reflections.
Okay.
So we take the whole triangle, all points of this triangle, under this reflection, they map to the points of this triangle. If you think about like this point, then it maps to this one.
Yeah.
And then we continue reflecting. We take this triangle and reflect it with respect to the next edge. So we obtain this one. Mm-hmm. And when I say that we are thinking about the like face triangle on this picture, I mean that we take each point inside and we reflect it with respect to the corresponding edge.
Oh, and I guess it's obvious from the construction that this is a continuous map, because as you get close to the boundary, then you're going to be close to the point you're about to get reflected to.
Yeah.
Yeah, okay. But it's not injective, as you can just see from the fact that the triangle you end up with is covering over W naught. Yep,
absolutely. Moreover, they said that like about this reflection, you can think about as folding of the t-embedding. So you can just take the whole t-embedding and start folding it with respect to each edge. So we take, for example, these three, and what's happened with this one? When we reflect it first time, this is the same as just to take this part and fold it along this edge, right?
Mm-hmm. And
then instead of just looking where this blue one goes under the reflection along this one, let us take both of them, this black one and this white one.
Yeah, okay, I see.
Yeah, like what is shown here, on one hand, this is just a folding along each edge. On the other hand, this is reflection of this one with respect to this edge and this edge, plus reflection of this one with respect to this edge.
Yeah. Okay, yeah, that's helpful. Thank you.
Yep. And so, yep. Let me give you one more definition of the origami map if you like differential forms more than planar geometry. Okay, so first let me define the origami square root function. So yet again, I associate to each face some direction. And the property for those is the following, that the product of their conjugate for two neighboring ones is parallel to the direction of the edge of the t-embedding. Okay, and why we call it origami square root function? Because actually it's not well defined, because if I go around the vertex, then we will see that this function is defined up to a sign. But the square is well defined. Why this is defined up to a sign? Because again, because of the angle condition around each vertex of the t-embedding. Because I know that the product of these two is the same as this direction, the product of these two is the same as this direction, and so on. And then when I will go around this one, I will see that here, instead of eta b, I should get eta minus eta b to have the correct direction. However, it doesn't matter because the square is well defined. Okay, so this is the origami square root function, and given note that this one is defined up to a multiplicative factor, right? Because I can choose at some point any direction, and then I can define all others just by this condition. Okay, so then one can define the origami differential form, which is defined by the following. So let us define a differential form on t-embeddings given by so it is eta w square dz for z on white faces of the t-embedding, and it is eta b square dz bar for z on black faces of the t-embedding. Then one can check that this is a closed form, and then the origami map is just the primitive of this closed form. And note that in this definition, it should be clear that the square of the origami square root function, so like for each white face w, eta w square, this is just the local rotation angle of the origami map on the corresponding white face of the t-embedding. So, and since the origami map is defined in this way, it is defined under the global prefactor, then I can choose eta w0 to be 1. And then this corresponds to fixing phase w0 in the previous definition. So this definition with eta w0 equal 1 correspond to the folding procedure, which I just described before. Okay. So is the definition of the origami map clear? Okay. By the way, let me maybe give you one more definition of the origami map. So recall that the t-embedding is defined by two gauge functions. And then the origami map is given by the conjugation of one of those functions. So why this is so? Just we can think about the origami map of the t-embedding as we just take all faces and we change the orientation of black ones and we keep the orientation of white ones, right? This is exactly what's going on under the folding. When you fold the plane, under like one folding, you have the orientation of white one is the same and the orientation of black one, it just changed, right? You just fold it. Folding is the same, or reflecting is the same as changing the orientation. And if you think about it in this way, then it's clear that the origami map is actually just given by the pair F and G bar, G conjugate, instead of F and G. Okay, anyway, if you got at least one definition of the origami map, that's good enough. I gave you a few different, I hope that at least one of them was clear. Okay, so now, sure.
Before we move, I have a question. So this definition is probably clear, but it's abstract. Is there any simple case where the origami map is explicit? For example, if you take, I don't know, an hexagon with all a regular hexagon with
okay, let us think about square lattice.
Mm-hmm.
Just a regular square lattice,
Okay.
Z2. Then first of all, it's clear that it is a t-embedding, right? Because each angle is just pi over 2, and clearly we can color it in black and white and so on. Now, if you fold the square lattice, if you do the folding of the square lattice along each edge, then you just get a square, right?
Yes.
You just fold everything to a single square. Yes. So the origami map of the square lattice is just a single square.
It's a reflection.
So fix any face of the square lattice, and then the origami map with this fixed face, this is just this square.
Okay.
So yeah, like this is the same for any regular lattice. If you start with a regular lattice which can be colored in black and white, then under the origami map, you will end up with a single face of this regular lattice. Another example is just shown here. If you start with this one, if this is your t-embedding, then here is the origami map of this t-embedding. This is the origami of this small graph of this small t-embedding with just 3 faces. And this is another way to see that the definition of the t-embedding and the centers of the circle patterns are equivalent, because let us think what happened with the circle pattern under this folding, right? And note that the points of circle pattern are symmetric with respect to the corresponding center line. Therefore, they map to the, because this is the intersecting points of 2 circles, one with center here and another one with the center there. Then all points of the circle pattern are mapped to a unique point under the origami map. And what I can do, I can just do the origami, then I can pierce this origami map and unfold it. I will get some punctures on the t-embedding. And these punctures exactly correspond to the circle pattern realization. so for any t-embedding, there is a two-dimensional space of circle patterns, because to each point for the origami, which I choose, then I unfold and I get the circle pattern for the origami map. Okay, so as I said, there is no, at least so far, there was no uniqueness for the t-embedding on finite graphs. Even in the case of outer face of degree 4, we in general always have two different t-embeddings. So what about uniqueness in the biperiodic case? In the biperiodic case, if we ask the origami map to be bounded, the origami map of the t-embedding which we constructed from the biperiodic graph, if we ask the t-embedding to be, or the origami map to be bounded, then there exists a unique Thatcher t-embedding. And by the way, also it is clear from what I just described that the boundedness of the origami map is clearly equivalent to the boundedness of the radii of any circle pattern. Just because of the construction, the radii of each circle pattern here, this is just the distance between peaked point and the vertex of the origami map. Okay, so for bounded origami maps in the biperiodic case, there is a unique t-embedding. Okay, so I gave you the definition of important objects like t-embedding itself plus the origami map. We discussed a bit the existence of such embeddings. Now, what about scaling limit results? So let me introduce some assumptions under which we can prove the convergence of fluctuations to the Gaussian free field. And here is assumption number one. So we say that the t-embedding satisfies the Lipschitzness assumption if the corresponding origami map is Lipschitz with a constant less than 1. Which means the following. So for any 2 points on the distance at least delta, the origami map satisfies the Lipschitz assumptions with some fixed constant less than 1. So now I need to introduce a mesh size, since we're going to think about scaling limits. And the delta here, this is exactly our mesh size. So we think about this delta as a definition of the mesh size. And now I have a sequence of t-embeddings. And now we have a sequence of t-embeddings, and we're interested in limiting results when delta goes to 0. From under this assumption, if the t-embedding satisfies this assumption, then it is clear that all faces have diameter less than 1, less than delta. Sorry, because if it has diameter more than delta, then under the origami map, if we think about it as a folding, those 2 points stay at the same distance inside this domain, so it doesn't specify this one. But let me emphasize that actually the size of faces could be much smaller than delta. So there is no assumption on that side. They're all smaller than delta, but we don't. They can be extremely small. Okay. The second assumption which we need is that the t-embedding satisfies the exponential fed assumption. So what is this? This is the following. Let me just, instead of giving a formal definition, let me say what does it mean in words. In words, it means that if you look at the t-embedding, then there is no face, there is no point inside the t-embedding, which is surrounded by faces of a very tiny size. So this is what I want our t-embedding to satisfy. Okay, of the size which is much smaller than delta. This is what is written here. Okay, anyway, this is an important assumption. This is kind of a technical assumption. However, we cannot get rid of this one, but let me keep going here. Okay, last time we discussed discrete holomorphic functions on the square lattice, and as I mentioned, it was the main tool for proving the convergence in two-dimensional, to show the conformal invariance of the scaling limit of two-dimensional lattice models. So here is the definition of holomorphic functions, of discrete holomorphic functions on the t-embedding. Okay, so let us define a function on black faces of the t-embedding in the following way. First of all of them are complex. All values of this function are complex, and they have a prescribed argument, which is the origami square root, which we already defined. So recall that here is the definition of the origami square root. So I say that the function defined on black faces is discrete holomorphic, is t-holomorphic, if it satisfies this condition. So it have a prescribed argument, and also it vanishes along each white face. So if we consider the discrete contour integral along the white face, then it is vanishes. Or in other words, this function is in the kernel of the Kasteleyn matrix given by the origami map, given by geometric weights of the, sorry, not origami map, of the t-embedding.
Wait, sorry, just remind me, what is B, uppercase B? Is this just the domain?
This
or is
one.
this the black vertices? No, B.
So B is a black word.
Yeah, uppercase B on the previous line. Is this the set of black vertices?
So yes, this is a set of black faces, and this is.
Yeah, okay, sorry, faces.
Yeah.
Okay.
So yeah. And okay, so we define the function on black faces that satisfy these two conditions. So it is in the kernel of the Kasteleyn matrix, and it has some prescribed arguments. This definition is the generalization of s-holomorphicity introduced by Stanislav Smirnov in the Ising model. For those who know, for those who don't, okay, this is just a generalization of some important object in the Ising model. And the main why this is a good definition for the dimer model, because if we think about the inverse Kasteleyn matrix, then the inverse Kasteleyn matrix is a t-holomorphic function considered as a function on black vertices. This is the same as we discussed last time on the square lattice. So for this definition of t-holomorphicity, K inverse is a t-holomorphic function. And under the assumptions for the t-embedding, which I just described, we can show that we can show a priori regularity of t-holomorphic functions. So even more, for bounded t-holomorphic functions, they are uniformly Hölder, which means that t-holomorphic functions in the limit, they are good objects. So this definition of discrete d-bar operator is a good one, at least in some cases. That discrete holomorphic functions converge to two holomorphic functions. Okay, So recall that last time I was talking about the nice definition of discrete holomorphicity on t-embeddings, and here it is. Yeah, so let me skip this one. However, it is an important part of the proof, but let me just emphasize let me state the main theorem and then emphasize the difference with known results. So assume that we have a sequence of t-embeddings which satisfies assumptions which I just described. So the origami is Lipschitz with the constant less than 1, and it satisfies some exponential fat assumption. Now also let us assume that first of all the origami map vanishes at the limit. Then let us assume that the inverse Kasteleyn metrics are uniformly bounded, and also that the correlations are vanishes, that the correlations of the height function vanishes on the boundary. Then under these two assumptions plus these three assumptions, we can show the convergence of the fluctuations to the Gaussian free field. So let me now say a few words about these three assumptions. The first assumptions cannot be completely dropped. However, we can get some results in more general setup. I will say a word about it a bit later. So the second assumption seems to be natural from the discrete complex analysis perspective, because if K inverse are not bounded on compacts, then they typically contain a local exponential growing factor. And then in such a situation, one shouldn't expect that the discrete conformal structure of t-embeddings captures the behavior of K inverse in a correct way. And the last assumption is quite natural from the Daimer model perspective, right? Because this is just tell us that the fluctuations vanish on the boundary. This is exactly what happened with the fluctuations in the Daimer model. Okay, so as I said, the first assumption cannot be completely dropped. However, similar analysis can be done using the assumption that the origami map converges to the Lorentz minimal surface. And about two other assumptions, in the case of perfect t-embeddings, I will tell you what is it. We're able to prove the uniform boundness of K inverse up to a boundary. And this easily implies the required estimate for the this just imply if we know the boundness, the uniform boundness of K inverse up to a boundary, this immediately implies that the third assumption satisfies as well. So in the case of perfect t-embeddings, we don't need to assume these two. They're just immediately holds. And what are the p-embeddings? So the p-embeddings are embeddings with the following boundary conditions. First of all, the polygon, the tangential, the outer polygon asks to be a tangential one. So there is a circle inscribed into this polygon. We don't want it. It doesn't have to be the convex one. the second condition is that all edges adjacent to boundary vertices lies on the bisectors of the of the boundary. And recall that outer degree 2k the project Kasteleyn and Sanjay, we can show the existence of relations. However, we check that they give a proper embeddings. Here, if I add these boundary conditions, we don't know anymore.
Let's see if she can connect back.
Do you hear me?
Yes,
Yeah.
now.
Okay. Yep. So in this case, we don't know how to show the existence of such a of the solution of this nonlinear system of equation. So we don't know how to show the existence of perfect t-embeddings. However, if someone tells us that such embedding exists, then we can check that it gives a proper embedding. So the perfect t-embeddings are always proper embeddings. About uniqueness, they're not unique. However, they're unique up to such. Okay, if f and g gives a perfect t-embedding, then this pair also give a perfect t-embeddings. And the perfect t-embeddings are unique up to this transformation. And yep, as I said, the existence of perfect t-embeddings, we cannot show it. However, we believe that perfect t-embeddings always exist for any given bipartite graph with any weights on it, on edges. And here is the generalization of the previous results. So in the case of perfect t-embeddings, just under assumption that the t-embedding satisfies this exponential Fed property. And also the second assumption, which is, however, not easy to check, but if we assume that the origami map converges to a Lorentz minimal surface, then we can show that the height fluctuations converge to the Gaussian free field in the metric of this Lorentz minimal surface.
Sorry, what do you mean by the origami map converging to a surface?
Okay, so note that about the origami map, one can think as a surface in R2+2, right? You can just take the t-embedding, and then under this t-embedding, you can construct a surface where the coordinates in R2+2, those just the coordinates of the t-embedding plus the coordinate of the origami map.
Yep, okay.
So then we have some surface in R2+2. And so yes, in this sense, the origami map converges to the Lorentz minimal surface in R2+2. Okay. And we will get the metric of this. We will get the Gaussian free field in the corresponding metric of this Lorentz minimal surface.
All right, thanks.
So, and let me just finish with saying that t-embeddings are actually generalization of the following known embeddings. First of all, it is a generalization of isiradial graphs, and t-holomorphicity is the generalization of discrete holomorphic functions on isiradial graphs. Then this is also a generalization of s-embeddings introduced by Dima Chilkak for the Ising model. And then if one think about the map between the Ising model, Dybeda map between the Ising model and the dimer graph, then s-embeddings of the Ising graph correspond to the special type of t-embeddings for the corresponding dimer graph. And the next object introduced by Kenyon and Sheffield is the construction of t-graph embeddings introduced for the dimer graph. And this is also can be seen as a generalization of t-graphs. However, as I decided to skip the slide where the following statement was made, that the sum of origami map and t-embedding